Thank you very much for the intro. It's been a great week already, and I was at a DOE storage conference last week, and interestingly enough, I heard the words last week, count key data, and this week I heard Christoph last night say the word channel program, and so I feel like I've been on the merry-go-round and I've come back around again. So anyway, let's get started. I've got a fairly long talk, so I want to get it in. What is Los Alamos? I never really know how many young people will be in the crowd that don't really know what Los Alamos is. I think there are probably history books now that have been written that gloss over the whole thing. But Los Alamos is where the nuclear weapons community began and where the nuclear weapon first was developed. In fact, it's interesting. The last speaker talked about John von Neumann, and I actually have a picture of John von Neumann standing right there next to Robert Oppenheimer in front of the machine he built at Los Alamos called Maniac, which was a machine right after ENIAC. And interestingly enough, we ran the first problem on ENIAC, which was the first machine in the US. And my mentor actually was one of the programmers, and she had the box of cables that she used to program that machine in her office, and she was quite a character, a wonderful role model. Anyway, so this is sort of what we do. We tested in Nevada for a number of years. We have a number of non-critical test facilities, a hydro facility, a neutron beam facility, and so forth. And the whole idea is to make the world safer from nuclear weapons and make them safe to use if we had to use them, and safe to roll them around, and so forth. So that's what we do. We've been computing for an awfully long time. As I mentioned, Maniac was roughly the third machine in the US. It was a big tube machine. Had a machine called Stretch, which is interesting. It was the forerunner to what was to become the IBM 360 series. It was considered to be a colossal failure. It was supposed to be 10x faster than Maniac, and it was only 4 times faster than Maniac, and IBM said, God, that was really bad. And then they ended up making their living off of that architecture for the next 30 years. The first Cray 1 came in to Los Alamos and didn't work for 6 months. It worked great in Minnesota. It didn't work at all in Los Alamos. Why? Because we're 7,200 feet in the air, and we have a few more cosmic events than you have at sea level. And so we had to ship the memory back, and they had to add some sort of protection to it, which is interesting, and we still suffer from those problems today. Lots of YMPs and XMPs. The CM2, the CM5 was interesting. For those of you that watched Jurassic Park, you'll recognize that machine, but that was actually the first top 500 machine on the first top 500 list ever, which is kind of interesting. It was, I think, about 1,200 sparks. And then other machines that we've had over the years, including our current machine, Trinity, and we've got a D-Wave quantum annealing machine, which if you're into quantum effects and things like that, which it sounds like our last speaker would love to delve into that, then there's a machine for you. And then we're in the process of buying a new machine called Crossroads to be installed in 2021. So anyway, we've been at this a really, really long time. Some interesting storage projects and products that we've been involved in. DOE or LANL has had a whole lot to do with, either wholly funded or not completely wholly funded. The list is pretty large, but we had a whole lot to do with all these essentially. And I'll take you through some of that later. The one in the bottom corner is very interesting. It's an IBM photo store. There were 4 of those made, one for NSA, one for us, one for Livermore, and one for the Census Bureau. And IBM thought that that was all the storage they would ever build in the world at the time. Those were microfiche, and you burned 1s and 0s on the microfiche in a barcode pattern. And there was a robot the size of this room roughly that was full of these little microfiche thingies. And my predecessor that ran the division used to say you could tell when the computing people had a really good night, because you'd come in and the whole place would smell like plastic burning, because they decided that's good data, we want to store that, we want to keep it, and they would essentially burn whole bunches of plastic to get all those data stored. Anyway, hopefully you recognize some of those names on there. So a little bit of background, quick, how we do things at the lab. So we have one big premier machine typically. It's Trinity, and I'll tell you more about it in a minute. It has a local scratch file system, about 100 petabytes, and runs at about a terabyte a second. And then we have a whole bunch of capacity machines. So the big machine, think 10 to 20,000 nodes. The smaller machines, think a few thousand nodes, and there's a whole bunch of them. And we run 2D and 1D jobs on the smaller machines, and we run big 3D jobs on the big machine. There's some site-wide scratch file systems that are available to this environment, so they're not private, they're shared amongst all the supercomputers. We've got a parallel archive. We helped develop HPSS. It's parallel tape, so you stripe data across lots of tape robots. And that's about 10 gigabytes a second, and the data is held forever, literally. We've got an NFS, for home and scratch and things, or home and project and things like that. We have a cluster set aside just for moving data, so you submit a job to the cluster, and it does nothing but move data for you, move a petabyte here, or move 10 petabytes there, or whatever. That's called the file transfer agent cluster, and then we've got some WAN stuff going to Livermore so that we can back each other up and so forth. So that's what our environment looks like, sort of roughly. The thing in the middle is our site-wide InfiniBand, essentially storage area network, and I'll tell you a little bit more about that in a minute. The largest machine is a 20,000 node machine. It's Haswell and K&L, a few million cores, 2 petabytes of DRAM, 4 petabytes of NAND flash that runs at 4 terabytes a second, 100 petabytes of scratch that I talked about before, which is a disk-based parallel file system. And then we have this thing called Campaign Store, and I'll get into why we have that in a minute, but it grows by about 30 petabytes a year, and it runs at about a gigabyte per second per petabyte. And then 60 petabytes of site-wide parallel tape archive, which actually is quite small, and we're not growing the tape very fast, and I'll get into that in a little bit as well. You see a picture of the machine. It's about a quarter of an acre kind of machine, and it's in the 10 to 15 megawatt range, so it's kind of a typical machine in its size. And then you'll notice that the pipes there, that's 36-inch steel water pipes. That's to hook the machine up. So the wires is one thing, but take the heat away is another. So that's the pipes that actually were put into the building to take the heat away from that machine. Unfortunately, those pipes full of water weigh an awful lot, and so I actually had to drill holes in the concrete floor in the basement, erect essentially a bridge and hang the thing, or it would have crushed the concrete. And so it's the really big pipes. Anyway, so, and that sort of stuff costs a lot of money, which I don't like paying, but anyway. So I want to take you back a little bit through history, and then later on I'll hopefully point towards the future. This was sort of a battle early on that I was involved in the middle of my career, roughly, circa 1994, 95. On trying to get mass parallelism implemented at the laboratories and in HPC environments. And essentially at the time we basically got together and said, okay, well, we want to build these crazy clusters with thousands of nodes in them. How are we going to do I/O off of them? And we didn't really know. And so we actually had a conference in this time frame, and it was called the Intergalactic Parallel File System Conference by Peter Braun. And there was a bunch of luminaries there. Garth Gibson was there, and Peter Braun was there, and Roger Haskins from IBM was there. And essentially, we ended up trying to start multiple projects to get this problem solved. One of them was Panasys, so we essentially got together with their venture capital and partnered up to try to get them started. We helped move IBM from what was then called PIOFS into now is what's called GPFS, but we had a whole lot to do with that, including writing some pretty large checks to make that occur. We actually started some interesting work at City, at University of Michigan, Peter Honeyman's group, to invent what became what is now known as NFS version 4 and PNFS. In fact, we funded the first prototype of that work that was done actually at Sandia Lab. And so that's moved forward. That's interesting work, compound RPCs and all the wonderful things they added there. We wrote a contract to University of California, Santa Cruz, and started this thing called Ceph, and I've got an interesting story about that I'll tell you about in a minute. We issued the contract in 2001 to start what is now known as Luster, and I spent 4 years of my life every Thursday morning with Peter Braun trying to get that thing to work, and it finally did, I guess, sort of. It's used quite a few places. In 2001, we had to invent this thing called the parallel scalable backbone to connect the multiple supercomputers to the multiple parallel file systems, which was an interesting concept at the time. To build a terabyte per second network back in 1995 was tough, and so anyway. And then In 2009, we did this thing called parallel log structured file systems, which I think has changed a lot of thinking in this community, in the HPC storage community, and I'll tell you about that in a minute as well. This is my Ceph humble start story. So we wrote this contract to University of California, Santa Cruz, Darryl Long, and that bunch over there, and we told them we wanted them to study scalable metadata in parallel file systems, and we all wanted them to study scalable security. Security has this, in POSIX file systems, has this hierarchical, unscalable thing about it, and we wanted them to study how you could get over both of those things. They came back and said, we want you to pay us to write a user space object-based parallel file system that is prototype, so that then we could go and play around with these ideas that you have about how do you scale metadata and how do you scale security. And we said, okay, fine, take the first 3 years of a 9-year, $300,000 a year contract to do that. And then the last 6 years, we'll study these problems that we really have. And there was this guy there named Sage Wild. He was a graduate student, and we ended up with what's now known as Ceph out of that, and Rados, and a bunch of other things happened. Interestingly enough, they took a run at scalable metadata, and that branch still, I think, exists in Ceph, and I think they're dusting that off now that they're back in the file system business and trying to use it. The other thing we gave up on, it never happened. So it was kind of a mid-level success for us, but it looks like it changed a lot of things for the world, which is great. 2 HPC I/O patterns that persist. So there's lots of HPC patterns that exist today. In fact, some of them that actually do quite a bit of reading, but in our world, we do a lot of simulation, so we do a lot of writing. There's 2 kinds of patterns that dominate. One is every process drops a separate file into the same directory. So think a million cores, and they all decide they want to drop a file into the directory, a single directory at the same time. So they all just run up within milliseconds of one another and beat the hell out of the metadata server until it gets all the creates to happen into that directory, and then finally you can start writing data. And it creates millions and millions and millions of files as it runs. Then there's end-to-one, which is all million cores decide they want to write into the same file, so they all open the same file, and they all offset in slightly different patterns, and they write, odd amounts, not necessarily the same amount, completely unstructured and stuff. So that's great on the metadata server and just beats the hell out of the data servers. And so either end of the spectrum is kind of hard to deal with, and we've been dealing with for a number of years, and I think we finally beat it into the ground, and I'll take you through how I think we did that. We also published a document recently, which I think is interesting, associated with an RFP that we were involved in, and that is for Crossroads. And we did this for Trinity as well, the machine before. And it was essentially a set of workflows. How do our applications run? What is the input sizes? What are the output sizes? How long does the data have to persist? And so forth. And that's interesting because the persistence, we needed a taxonomy to deal with this, and to tell vendors, here's what we're trying to do with your machine for the first 5 years of its life while it's at Los Alamos. And so this is what we want to do with it. Can you help us build a machine that will work well in this environment? So this document is interesting, and it's published, and you can go find it on the web. The parallel file systems, again, I talked about being able to connect them to the different supercomputers that we had. And so this was a long time ago. Back in 2011, we had a terabyte per second network that connected them together. And essentially, it was taking a whole bunch of metropolitan area network switches and connecting them together into interesting ways to try to get, load balanced and failover to work at the scale. Today, things are much, much larger. Think about 10 terabyte per second networks to connect machines together, which is a lot of wires and a lot of switches and a lot of things to go wrong. But we do this sort of on a daily basis. Well, enough with the history. Let's talk a little bit about some economics. So in 2009, so we were, during the late 90s and early 2000s, we were running along fine. We had Lustre working, we had disks we were buying. We'd buy enough disks to get the bandwidth we needed, enough disks to get the capacity we needed, and everything was wonderful. And then I started running economic models. And I'm particularly proud of this one. The story I tell about this is it's the first economic model I ever did where $1 million was on a log scale, which I thought was pretty cool. Because I couldn't think of any other way to show it. So this is essentially, me predicting what size machines we're going to have, how big their memories are going to be over the years, and how many disks and sort of media we were going to have to buy to keep up with the bandwidth and the capacity concerns. And it looked like basically what was happening. We were, a long time ago in the 90s, we were buying enough capacity and getting the bandwidth for free. And as we moved forward, we ended up buying disk drives for bandwidth and getting the capacity for free. And of course, disk drives aren't priced for bandwidth, they're priced for capacity. So it looked pretty horrible from a millions of dollars point of view. So we, did the thing that all good storage people do, and we said, let's throw tiers at it. That's what storage people do, is use tiers. And so we said, there's this thing coming along called flash. Let's inject that flash layer and see if that helps. And sure enough, it does help. The blue line there is the bottom line, which is, a hybrid system where flash you use for bursts and disks you use for capacity. And you notice that there's a crossover point back in 2012. It actually didn't happen until about 2014, but it did happen. And so, anyway, we came up with the idea that we were going to have to inject a layer. We called it burst buffer, and we kind of wish we hadn't, but we did. And we did the same economic model for the tier below it, which was this parallel tape tier, and below our parallel file system. And always before, we were modeling, our archives, and it was essentially archives equal the cost of the media. And that turned out to not be true. There were 2 years that kind of popped out as the new tape drives ended up costing more than the media, and we started asking ourselves, well, why is that? Well, that turns out to be when we were going to buy big machines that had way, way more memory than the last machines we had. And so the sizes of data sets that we had to store on tape were going up and up and up. And so now we're talking pushing a petabyte, and that's a big data set to store tape, even lots of tape drives in parallel. And so the bandwidth started getting us in the tape arena as well as the disk arena. And so we ended up saying, well, gosh, we're storage people. I know what we'll do. We'll inject another tier of storage in here. We'll call it cheap disk storage, and we'll use that for putting our really, really big things on where we need more bandwidth than we can get from tape. And that's what we did. We call that campaign store, and I'll take you through some of that in a minute. The burst buffer hoopla parade. So I walk into the supercomputing and in 2014, it's like, I don't know how many, I've been to 25 of them already, and I walk in and, they're setting up all the booths and everything, and all the storage vendors had this big sign, burst buffers, get them here, right? And I just looked at my shoes and went, oh my goodness, I named it the wrong thing. But anyway, 2 products, 3 really, but two products exist today. DDN's Infinite Memory Engine, which is essentially a tiering solution, and Cray's Data Warp. We use Cray Data Warp at Los Alamos. They also use it at NERSC. They have had really good success at NERSC, and we've had good success at Los Alamos using Cray's Data Warp engine. And essentially, it's just a tier of flash storage that sits in between memory and disk. And we use it primarily for bursting of checkpoint restart data. NERSC uses it for all kinds of cool things. So let's talk about all these tiers. They're not necessarily great for the user, but they're sort of economically a reality. And back before Trinity, we had 3 tiers. We had memory, a parallel file system, and an archive. Now, after Trinity, we sort of have 5 tiers: memory, burst buffer, parallel file system, campaign store, and archive. I put up there sort of the residency times and the sizes for the current machine and the speeds for the current machine. It's sort of roughly about an order of magnitude difference in the bandwidths between the tiers. And you can see that the tiers that we added were those 2. And I've made this prediction. This was sort of an eye-opening slide for a bunch of people a couple of years ago at supercomputing. I was giving a talk at the Seagate event, and I made the bold assertion that parallel file systems will hopefully leave the Earth at some point. And I don't know if that's really true, but what I meant was flash is getting cheaper faster than disk is getting cheaper on a per byte basis. And at some point, we'll be able to afford a far more flash and for what we do. And disk is going after capacity. That's its only play that it has left. And so it's going to get harder and harder to write to, look at the various kinds of disks that are out there today. They're getting harder to write to, but they're But they're okay, easy, relatively easy to read from, and that's just going to get worse probably with patterns and other kinds of things. And so it looks very much like disk is going to be the solution for capacity, and flash is going to be the solution for anything but capacity, bandwidth, and or IOPS. And so it's likely that it will sort of press out that high performance disk tier that's in the middle there, and they'll just be low performance disk and flash, and that's all there will be. And in fact, our RFP for the next machine in 2021 more or less says this. So instead of having 3 tiers, having flash, parallel file system, and slow disk, we'll just have flash and slow disk. And of course, we'll have more flash. So think more like 10 or 20 petabytes instead of 4 petabytes, and faster, obviously. So anyway, that's a prediction. I don't know if it'll come true, but it looks like, at least for us, it will by 2021. So this tier here, this campaign tier, this capacity tier, how are we going to provide that tier for us? And so we, from a software point of view, it's cheap disk. How are we going to use it? And you might say, well, shoot, cheap disk, that's easy. Just go buy an object server. Well, we tried that, and it's wonderful for a while, but we have this problem that we wanted low cost hardware. B, we wanted object or some kind of massive scaling. The problem is, A, it's got a really simple-minded API, get, put, and delete. When you're trying to put petabyte-sized files, where you really need at least get stream and put stream and a few things like that. It's really hard to do otherwise. And we've got apps that we've spent trillions, literally, of dollars on that expect POSIX and files and actual folders and not just fake folders and things like that. And so there's people out there, there's lots of trillions of dollars worth of applications that still need some folders and things like that. Some POSIX-isms, not the whole thing, but at least some. We couldn't really find a decent solution that would solve both problems, that would give us enough POSIX-ism and enough object-oriented scalable parallelism. And so we looked. In fact, I have this whole slide of all the things we tried and looked at. It could have been Ceph perhaps, but at the time, Ceph was trying to become the best server of virtual machine boot disks, which is great use of it, but at the time it wasn't really solving the problem. We looked at Gluster, we looked at all kinds of things, and a lot of these things that put file systems on top of objects are pretty anemic. I mean, they'll take flattened namespaces and try to make a hierarchy out of them in odd ways and things like that, and it just sort of works. And so we decided we're going to have to write our own, unfortunately, and so we did. It's called MRFS. There's a talk later in the week about it, so if you're interested in massively scalable POSIX on top of object, I'd recommend you go. Anyway, it's trying to be the best of both worlds, use objects, but use scalable POSIX file system sort of semantics for the metadata. I'm not going to go into it again because there's a talk about it. Here's some of the requirements that went into it. So we're basically talking a few hundred gigabytes a second to a few terabytes a second. Billions of files in the same directory, trillions of files total. This, of course, was 3 or 4 years ago. These numbers have gone up. Near POSIX, not total POSIX. And we tried several things again. And anyway, the idea was let's build something small, highly leveraged, and open source it and see what happens. We've been using it in production for a couple of years, and we like it. And you're welcome to get involved if you want. But what it isn't, it's not complete POSIX. So you can't do, like, for example, update in place, or you can't do various things like that. So we shortcutted a few things to make it easy. It is small and lightweight and very leveraged. You might ask, okay, how do you move data to and from these big machines and big parallel file systems? Well, a long time ago, I actually wrote the first one of these, and it's been rewritten like 7 times, I think. Is a tool called PF tool. It's interesting in that it has parallel reader, parallel stat, and parallel copy, rsync, and compare. And so you basically just point it at a tree and say, here's a trillion files and a few petabytes, move it over there. It's restartable, so you can just keep restarting it until it finishes. It'll even restart if it's moving a single petabyte size file because it knows what chunks it's sent and it will restart. which is kind of cool. So it's pretty neat. It's completely load balanced, so it'll just use what you know, whoever's the fastest. It's completely asynchronous, so it may write a file backwards if it has to get the data moved. And so it's interesting, and it's also open source, and feel free to come get it. How does this campaign thing fit in our environment? Well, it plugs into our terabyte per second storage area network, and it's available for people to use. People essentially use it through these file transfer agents that I talked about. Okay, so we're running this thing along for a while, and we got a whole crap load of disks. And what happens to us? Well, so it's an interesting story. We're sitting in a pretty room with a big window that's looking out over this billion-dollar machine room with all this crap and all these fans and lights and stuff blinking. And we're having a meeting with Seagate of all people, and we have this interesting brownout, and we lose 441 disks in the same day. And 441 disks in the same day for the population isn't really huge, but it's still quite a few disks to lose. And so we started talking about how we're going to solve this, and we started modeling it, and actually John Bent at DDN helped us model some of this. And we were using erasure and a single tier of erasure, and we decided we're going to have to go to 2 tiers of erasure. And you can see the difference at the bottom. Those 2 bottom curves on number of simultaneous failures are, and for different scenarios, 22 plus 8 and 44 plus 16 and 170 plus 70, which actually is pretty good, but that's crazy to calculate. And then we did this 2 tier, which is 10 plus 2 on top of 17 plus 3, which turns out to be what we use now, and we really, really like it. And there's a talk about it, and so I'm not going to go into it any further. This is kind of what it looks like. It's a tier of erasure in parallel on top of a whole bunch of ZFSs. So the whole thing looks like just a crap load of ZFSs, 17 plus 3s, just a bunch of them. And then this thing does 10 plus 2 on top of it, and it's really pretty fast and pretty cool. And it's open source, so come get it. We thought about, well, gosh, if we wanted to use tape, what are we going to do with tape? And we're seeing this phenomenon with tape. The tape is expensive tape is kind of disappearing, and cheap tape is kind of all that's going to be left at some point, and so you're going to have to erasure across it to be able to use it. And so we think we've got a built-in solution for how to do erasure. Just plug in different tape systems down below, and just like we do ZFSs, and we instantly have a fairly inexpensive way to do erasure across tape. Let's talk a little bit about the future. Run through this really fast. So we think we sort of whipped scalable parallel data movement. We think we've beat it for 20 years and pretty much hopefully did. And so let's go after, well, let's add value to the data. Let's concentrate on metadata primarily. We talked about VPIC for a minute. VPIC is a particle in cell code. There's a trillion cells and a few million cells and a few trillion particles. And essentially you run this application for a while. It runs, for weeks or something, and it's writing out these timestamps, and the timestamps it wants to write out is where was the particle at, which cell was it in, right? And it does this over and over again. So you think getting trillions of records every so often. It actually was written to write a file per particle per time step, so that's a trillion files per time step, which is fun for the metadata server. We decided that wasn't such a good idea, so we wrote a little library with Carnegie Mellon that made it think it was writing files, but it was really writing key value records into a parallel key value store that we had devised, running a few thousand copies of level DB. And it was pretty cool, right? So you're writing these records, it thought it was writing files, and then at the end it says, these 1,000 particles are interesting, and the first thing the scientist wants to know is, where were these particles at? Why are they interesting? So you could essentially just go in and do a query against it and come up with an answer, which was very neat. And so this is an example of how record-oriented store is likely to be in our future, which is very interesting because now I can say the word VSAM and I'll have really truly come back around in my career for 30 plus years. Let's not go through that. Let's go to the next thing. The next thing is MDHIM. MDHIM is, okay, that was really easy because it was a single dimension index. All I wanted to know was where the particle was. What if I wanted to know not only where the particle was, but what was going on around it that made it be a fun particle? And so that implies more dimensions of index. How do you do a multi-dimensional index? at this scale, trillions of things, and you're trying to keep 3 or 4 dimensions of index against it. And so that's what MDHIM and XDHIM is about. It's a project going on right now funded by the Exascale Computing Project at DOE and DoD. And the kind of questions you want to ask yourself is, okay, well, how would I track a wave through time? And this is an AMR calculation, so you can see that different parts of the problem resolve differently, because you only resolve really tightly where the fun parts are, and where the unfun parts are, you don't care how tightly they're resolved. So you're running this application, you're doing these time steps, but how do you, but it can change. So every time step, it'll look and say, well, you know what, the fun part moved, so I'm going to have to remesh this thing. And so how do you build an index when, that geolocates things when the geolocation is changing all the time? And so we thought about that a little bit, and we actually ended up borrowing something from Microsoft. There was a project called Farsight that essentially had this really cool concept of adding dots to the index, right, so that you can insert things in the middle. It reminds me of Fortran programming, adding zeros to the end of your column numbers. But at any rate, that's how the index works. So the index can grow and expand in various areas as you go, which is kind of interesting. And it actually is multidimensional. At current, it's 6 dimensions, but the whole idea is to be able to do things like track data through time. And then the last thing I'm going to talk about is, okay, we got all these file systems and all these storage systems, and they got all this damn trillions of metadata entries. How do you find anything at the laboratory? How do you find where your data is? And we've started building this piece of software called Goofy, Grand Unified File Index. And essentially the idea is we want to try to cross a file system and a database. And so that's what we did. And the way it works is we replicate the tree, the directory part, but not the file part. And then we take the file metadata and we put a SQLite database at every node in the tree. And then we do very, very wide breadth first searches that walk the tree in parallel, and very, very wide depth first search, or breadth first search threaded, and each one is doing an SQLite query, and the performance is just absolutely phenomenal. We've been totally amazed by it. So much amazed that on my little laptop there, that's actually a dual core, not a quad core, I built a thing with 250 million files, and I searched through the whole thing in 2 minutes. And it's way bigger than will fit in memory. I mean, it's way bigger. And so you're coming from a cheapo flash device on a little bitty old crappy 4-year-old Mac, and it goes this fast. Imagine how fast it would go on a real machine. We're actually buying a real machine to put it on, and we're hoping to be able to use this. This is also public domain, and you can come and get it. And I'm over time and done. That's not a picture of me, but I was actually there at that time. It's all public domain. It's all open source. I'm here the rest of the week. This is a great conference. Thank you for inviting me, and hopefully you enjoyed.